want to go ahead and do just a little bit more with our IVT because quite a few of you, as I walked around, said that you were struggling with that on your homework. So let's go ahead and just do a little bit more with that, and we'll go over homework. And we'll talk about that trip lab and then dive into limit definition of a derivative rating. Okay, so remember, IVT tells us that maybe all right, IVT has a couple of conditions that need to be in order before we can actually apply it. The first thing is that our function needs to be continuous. We have to have that our y values of our endpoints are different. Alright, our endpoints, y values have to be different, and the y value that we're investigating needs to be between our y values of our endpoints. If those conditions hold true, then we can say that there is some x value within my interval where the y value associated with it is that y value we were considering. So the picture here that we had is that basically as long as our function is continuous, it means it has to hit every value in between f of a and f of b, and likewise every value between a and b. So if we pick a y value in between that interval, then there must be an x value that's associated with it. That's the short function. Now, the special case that we talked about is if our y values change from positive to negative or negative positive, that means it has to cross 0 at some point. That's particularly helpful for us when we're investigating roots for x-intercepts or zeros, because our y value there is 0. So if we know that it crosses it, then that tells us that it exists, that there exists at least one root somewhere within that interval. Now, there could always be more than one instance in which we have that x value hit it, but IVT guarantees there's at least one. Alright, so the problem that we looked at, a typical type of problem that AP might give you is where they give you a chart of values, and the one that we did, it doesn't even tell you to use IVT, but because of what they're asking about, we know that we can use IVT because they're asking about us, they want us to investigate a particular y value, seeing if it's within that interval. They told us it's a continuous function, so we knew that to be true. We checked that our endpoints are not equal, as we can see from our chart here. And it asked, does there have to be a time in which the velocity is -3? And so we see that indeed it crosses our value -20 to 10, it has to cross -3 somewhere within there. So if it has to cross -3, that means it must be some time within this interval, 0 to 60 seconds, in which that occurs. Now we can narrow down this window, because we see from 20 to 35 seconds, it changes from -5 to 0, so it must cross -3 there. So we could even narrow down the window if we wanted to and say that there must exist a time between 20 and 35. But since they asked for between 0 and 60, we just went ahead and stuck with that. So let's just do one more like that B, and then we'll take a look at other ways it might ask you about that. So again, notice here our questions don't say anything about intermediate value there. So this is something where you need to be able to understand what IVT is asking or tells you and when to use it. All right, so for this next one, it says on that same interval 0 to 60, must there be a time when our velocity equals 8? So again, in order to apply IVT, we need to first see, is it continuous, which our endpoint's different, which we've already established, and does this velocity, this y value, fall between the y values in question? So going from -20 to 10, does it have to cross 8 at some point? Yeah, you got to cross it. Since it's continuous, and this is really the key thing, since it's continuous, it has to pass through there at some point. Okay, so again, we check our conditions. One, first of all, is the function continuous? And indeed it is, they told us this. So go ahead and write this down with me. V of t is continuous. And again, we've got to establish our endpoints are different. I know we already did it above, so I'll do it again for good measure. Alright, so my one endpoint has a y value of -20, the other endpoint has a y value of 10. And again, from -20 to 10, you must cross 30. Alright, so then the next key thing that lets you know whether or not you can use IVT is, does that y value fall between our endpoint y values? And it does. So we can go ahead and establish that v of 0, which we already said is -20, is less than 8, the point in question. which is less than our other endpoint, b of 60, which we said is 10. Alright, so we've met the conditions. It's continuous, our endpoints are different, and that y value falls in between. So those were all the conditions. That was all the part of your if statement. If you think back to geometry with your if-then statements, those are all the ifs. Then we can declare by IVT that the x value must fall within the x value interval. Okay, so thus, or therefore, or then by IVT. So thus, by intermediate value theorem, IVT, one of the few abbreviations AP exam allows. There is a C value. Because we don't know exactly what it is, so we're just going to say C value. You could have said Q value, H value. We're going to stick with C since that's what the intermediate value theorem uses. There is a C value. So that my C value falls in that X interval. So C is in between 0 and 60. And that C value, so we know, let's see, we're talking about 8, so 8 would be somewhere here. So F of C. We know that C value would have been somewhere within this interval. We'll again stick between the larger interval 0 to 60. And so that C value's Y value, so B of C, would have to be that. So we're questioning 8. It asks when B of T is 8. C is a specific T value that we're looking at. Yes, absolutely. AP exam wants to see each of these conditions. Has to be met before you can apply it. So you must state that it's continuous, you must check the endpoints, you must state that the Y value is in between the interval. Then after you've shown this to be true, then say by IVT, we can say the X value is in that interval and the Y value is going to be the Y value in question. Absolutely. Other questions with that? You know, as long as you've established that you should be fine. Sometimes what I've seen on the AP exam cases, they'll say B of 0 equals negative 20, which is less than 8. But as long as you've established it, that those are the values associated with it, you should be good.
You work with the first and second definitions like together, or if I use like B of 0 equals negative 20, and B less than 8.
Yeah. You could have, instead of saying this separately, say B of 0 equals negative 20, which is less than 8, which is less than B of 6 equals 10.
Is that one of them?
And doesn't really matter. Yeah. So you can totally combine this with that. It just sometimes starts to look like a really long, crazy statement that doesn't make sense. But that's perfectly fine. As long as you've stated what those values are and that it creates this inequality, then you're good. Other questions with that? I mean, basically, if it's continuous, it has to cross all those Y values and X values. So if there is a Y value in there, there's got to go an X value with it. Now, the further ones, or the ones further down, it's still using that IVT. It's just asking about specific cases. And here they even tell you to use the intermediate value theorem. Again, they aren't going to always do that. But they don't tell you what Y value to be questioning, which Y value to be investigating. This one, they tell us, well, does it have to equal negative 7? But down here, they tell you to use the intermediate value theorem, but it doesn't tell you which Y value to investigate. So how would we know? It's asking to show that the polynomial has a root in that interval. How do we know which Y value to look at? Which Y value do we look at? What does it mean to be a root? The Y value is 0, it crosses that x-axis. So in order to know that it's a root, and that means that our, let's see, that's f of x. F of whatever c is has to be 0, right? That's what root means. Same with root down here. We know it's a root if that Y value is 0, if it crosses that x-axis. Again, roots, I guess they use roots for each of those. So each of these, they didn't tell us what Y value to use, but they said root, and we know root means it has to have a Y value of 0. Alright, so it's going to be that same process. First of all, is our function continuous? Is f of x continuous?
Yes.
Yeah, why? It's a polynomial. You don't necessarily have to state why, just state that it is indeed continuous. Now, it's possible that you might have a function where it's not continuous everywhere, but as long as it's continuous on the interval, you're okay. Right? Now here it's continuous everywhere, so we don't have to specify exactly where it's continuous. But say our function was x equals 1 over x minus 2. This is not continuous everywhere. What value makes it discontinuous? 10. But notice for this interval, would it be continuous on the interval? So we would say f of x is continuous and specify which interval. Here it's continuous everywhere, so we don't need to worry about the interval specification. Alright. So now we don't have our endpoint values given to us. We do have to check those. We need to actually say what those are. So let's check that out. F of 0 and we need f of 2, because those are the endpoints that we're looking at. What is f of 0? Negative 3. That one wasn't too bad. F of 2 takes a little bit more work. Is it one? Positive? One. What is one?
Positive.
Very good. Okay. Do we agree with positive? Okay. So for this one then, we know that, so I mean we could do a rough sketch. We don't really know exactly what the graph looks like, but if I were to kind of investigate this visually to help us understand what's happening here, we've got f of 0 is negative 3, we've got f of 2 is 1. So if this is a continuous function, do you agree it has to cross the x-axis somewhere? That's what the intermediate value theorem is guaranteeing us. We don't really know what it looks like, but we know that at some point in time, if I'm not allowed to pick up my pencil between here and here, it has to go across that x-axis. Alright, so we got continuous, our endpoints are different, and the point we're questioning is in between those, right? Negative 3 to 1 does have to cross 0 somewhere. So let's do that. So again, f of 0 is less than 0, which is less than f of 2. Our y value, the point in question, is in between the endpoints there. Alright, so then we can go ahead and use IVT. We've met all those conditions. So by IVT, there is a C value so that, let's see, C is between 0 and 2. And f of C is 0. I don't know why we're struggling now. F of C is 0. And again, your little connecting words might be different. You might say, by IVT, there exists a C value such that 0 is less than C less than 2 and F is equals 0. Or by IVT, there is a C value where 0 is less than C, which is less than 2, such that F of C equals 0. That's fine, as long as you've conveyed those big ideas there. Your little connecting words might be different. The mathematical way would be to say there exists a C value such that. But as long as you've got that main idea there. Questions on that? So again, with example 3 here, again, it's asking about a root, so we would have to investigate those endpoints, see if those y values go from negative to positive, positive, negative. Same with example 4, does it guarantee roots? Again, check to see, does it change from negative, positive, positive, negative? Example 5, find the C value guaranteed by IVT. Here's it. All right. So it says find the C value guaranteed by the IVT. So now it's no longer asking, is there such a value that is true, but rather find that value. So we want to find f of C. So first, let's verify that we can indeed use IVT. First of all, is our function continuous? Yep, f of x is continuous. All right, and let's go ahead and check f of 0 and f of 4. What do we get for f of 0? Negative 13. And f of 4, 16 plus 16 minus 13. 19. Do we agree with 19? Alright, so would you agree that it has to cross from negative 13 to 19, that we've got to cross 8 somewhere? Yeah. So our y value in question. It's off, and then as I go to the bottom, it lines up with my prayers. Smartboard struggles on Mondays too. I think Friday isn't really every day of the week. All right, so we do indeed have that our y values cross. So we have f of 0 is less than our 8 that we're questioning is less than f. Do be careful. It's not always going to be that the left endpoint is smaller than the right endpoint. It might be the other way around. So just make sure you're setting up your inequality correctly. All right. So find the value of C guaranteed by our IVT. Okay, so we know that we can use IVT. We've checked all those conditions. So how in the world do I find what C value gives me 8? Yeah. And we want to know when f of c equals 8, so let's go ahead and put an 8 for our f of x value here. All right, so let's do that. So f of x, we're wanting to know when it's 8. I'm going to go and change these to c's. You could leave it as x's in the end, just say c equals. All right, what are we going to have to do here? I see a squared and a regular plain on c. Factor, 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 never goes away. All right, so we have c squared is 4c. Subtract 8 minus 21. What do we have this factor into? Good, plus 7 minus 3. So what do I get for my two potential c values? Okay, negative 7 and 3. Can I take both of those? Why not? Good. Gotta look at our interval. 0 to 4, negative 7 is not in that interval, so we take c equal to 3. All right. Any questions on that? So let's go ahead and take a look at our homework and questions we had on there. Let's start off. This was your first page. Any questions on that first page? Any questions on that back side? We're going to find those discounties. Yes. So we're wanting to investigate the limit. So everywhere except from one is this function here, right? So if we were to kind of draw out the picture, let's see, so it's been shifted right one. So it's going to look something like this. Probably, something like that. So it's defined elsewhere, but we're interested in the limit, not the point itself. So we're checking left-hand limit, right-hand limit, and for this, we should go ahead and have two different limits. You're checking your left hand. So if I check from the left-hand side, I take a value that's really close to one on the left, so let's say like 0.9. So 0.9 over, 0.9 minus 1 give me a negative, so we would get a negative infinity there. We know that with that asymptote, we're going to have either positive infinity or negative infinity, so an overall d/e. So I have negative infinity, d/e, and then coming from the right side, pick like 1.1, we get positive, so it'd be going to positive infinity. So regardless, actually, since it's a vertical asymptote, we know it's going to be going to an infinity. So it's going to be d/e regardless. So my limit from the left does not equal the limit from the right. And that was that second condition. That limit at that value, we don't, the first one's the specific value itself, but the second one's just the limit. Remember, limit, we don't care what the actual value is. We just care what's happening as we get infinitely closer to that value. So as I get infinitely closer from that side, it's going down to infinity. As I get infinitely closer here, it's going up to positive infinity, so we have the limit does not exist. So then we're going to have it's not continuous because our limit does not exist, but also those two. Other questions? Yes.
Can you G on the upper section?
On the same section?
No, the
Upper one. Yes. Alright, so we're looking for points of discontinuity here. Tangent, you can probably think of your asymptotes, right, to figure out what those are. But those asymptotes occur specifically when cosine is 0, because that's what makes the denominator 0, which then blows up the whole thing. So thinking of tangent, if you can't think of just what the asymptotes are, think of it in terms of sine over cosine. So then we're investigating when cosine is 0. That's going to be where my asymptotes are. Now, I don't think they gave an interval here, did they? No. So technically what this should say is infinite discontinuities at x equal to, so it's going to be, so if it's pi over 2, 3, every multiple, or pi over 2's every time around, right? So we can write this as pi over 2 plus pi k, where k belongs to the integers. Because it's pi over 2 out of pi, 3 pi over 2 out of pi, 5 pi over 2, so on and so forth. If they gave us that interval, looks like here they just stopped at 2 pi, then you can stop with an interval, but technically it should stay all that. Integers, have you guys seen this notation before? Yeah. Do you remember what the integers are? Think back to like middle school. What makes integers integers? They are real numbers. Can I have 2.2? Why? It's not a whole number. So basically it's our whole numbers with the negatives. So negative and positive whole numbers including 0. Yeah, so what this says is pi over 2 plus pi k, where k belongs to integers. So basically what you're doing is you have pi over 2 and then add 1 pi. 2 pi. Oh, yeah, so this is, it's kind of like, you know how your real numbers is like an R with 2? It's like a Z. It represents the integers, don't ask me why it's Z. Yes?
I'm confused on letter F.
Letter F on this section?
Yeah.
Okay.
I'm not sure what that is.
So here we have square root, so we know it's continuous on its domain, but the problem is its domain is not all real numbers, so we've got to figure out what its domain is. We know for radicals, the restriction is that what's underneath has to be positive or 0. So we go ahead and take this, what we did in class is we went ahead and set up as an inequality. We know it has to be greater than or equal to 0. We're okay with it being 0 because it's not in the denominator. So then we would solve and get x is greater than or equal to negative 5 or negative 1/2. So that means everything bigger than or equal to negative 1/2 is good. It's fine. So then that's why we include that. Remember we talked about continuity at an endpoint means that the limit as you approach it is the same as the value. And if we think of our square root curve, just normal, that limit as you approach it is that value. So we do include the endpoint. It's allowed to be that endpoint. And then does that make sense? Other questions on this? And I think we started dealing with piecewise. Okay. Questions on piecewise?
That
The steps with a million different pieces to it. Okay, so in our previous ones, we only had 1 point in question, 1 point that could cause that potential issue. With F, we've got 2 different spots where we might have an issue. So at x equal to negative 3, there is that potential for a jump, a hole, or a break, or an asymptote even. And then also at x equal to 5. So we want to make sure it's continuous at 3, because we know 4 is continuous everywhere. We know that this polynomial will be continuous everywhere, and this will be continuous. So it's continuous, 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 but that point in which it matches or maybe doesn't match up is where we want to see if it is continuous. Now here we're establishing the values that will make it continuous. So I want whatever this is and whatever this is to be equal at negative 3. And then I want this and this to be equal when x is 5. So that's why we've got these 2 different equations. So 4, I want these 2 chunks. 4 equals bk plus k at x equals negative 3. This is what we want. And again, use that. I know it seems silly to write 1. That's what we want. And then our second part, we want our bottom two, and that's bk plus k, to be equal to the negative 4. And we want this at x equals 5. Because then that means that we're getting those graphs to match up so that it continues to be continuous over here. So really what we get then is a system of two equations. So let's see, what did we do here? Went ahead and solved for this one in terms of k. So we substituted the -3 for x over there and the 5 for x over here. And then got it down to these two equations. Take this, substitute it in for k, and then it's just a system of equations from there. Yes?
Did you just make like directly here and plug in for k in the second one? So like you found k equals 1.
Oh,
And
yes, but we had to first do substitution before we could find that. Either substitution or elimination.
oh, so,
So it's like we went from here over here, found b, and then, but you could have gone the other way. You could have solved for b, substituted it in. Just a system. Other questions on this page? Okay. And then I think we're left with IBT. So again, remember IBT, we need to establish that it's continuous. We need to show that our endpoints are different, and we need to write out that y. So here on this key, both specifically what you're asking about, we could go ahead and state those endpoints within that term to knock it out in one thing.
okay, that's not correct.
Yeah, that's perfectly fine. So questions on the back side here. Again, this first one, we're investigating that 30. We see that it doesn't even have to cross 30. B, well, how did we know this? It says the minimum number of times the UPS truck stopped. What does that mean if the truck has stopped? What is its velocity?
Also 0.
It's got to be 0. So we're looking again for that change in sign. Oh, wait, this is a mistake. Did you guys get 3 times? Anybody get 3? Okay, so it should be 3 times. We found this last class. So we had, it goes negative, negative, negative here. It goes positive, so it had to cross there. Positive, positive to negative, had to cross there, and one more time. So we actually had 3 times.
Oh, wait, when the truck stops, you're looking for this flipping side.
We're looking for stopping means that the velocity is 0. And we know that it crosses 0 when it goes from negative to positive or positive to negative. So basically, going from negative 10 to 25, I had to cross 0. Right. And then I think there are quite a few roots after this. So 2, again, root, so that's when we're looking where f of x is 0. 3 was a root. Again, f of x is 0. Root. All right, questions on this one? Yeah. Oh, you know what? There was one like this on the notes. So this one, it should say, because it should be presented in a function notation, and this is an equation. So it should have said, instead of this equation, f of x equals 1 minus x minus q. You should not, because it says to show the polynomial function, but the function should not be an equation. So it should have been written like that. I apologize for that. So again, looking for that root in the interval, we want to know if our y value ever is 0 here. Again, test those endpoints. F of 0, we get 1. F of 1, we get negative 1. So we have it does cross that 0 at some point in time. And it just wants to determine whether it does. So again, we have it's continuous. Cube root, there is no restriction on that, right? Even roots, there are restrictions. Cube roots, no restrictions. So we have it's continuous. Our endpoints are different. And that y value we're questioning, the root at 0, is in between our endpoints. So there must be some c value that's within our x. That would you look like questioning. Do you have a question with the processing?
On 5 and 6, don't make this big as continuous.
Yes, you should.
And so
Each time, actually.
on 6, would we say f of x continues on We have to say on file.
Yeah, so that's a great question. Here, you want to go and specify it's continuous on this interval in question,
Just
because it's not continuous. Yeah, very good. Other questions on this? All right, let's go take a look at that Trip Lab project, kind of talk to that real quick before we get going with notes. So this is your first of projects throughout the year. And this is going to get you to kind of investigate the concept of Riemann zones and what they are. That comes into play a little bit when we start doing intervals. All right, so you and one or two classmates are going to go for a drive. Now, please choose the responsible one to drive. Or you can have an adult drive for you. Preferably don't choose the people that drive on the wrong side of the road. All right, so either have an adult drive for you so you don't have to worry about that, or have someone that is the responsible driver with a clean record driving. But the person that's driving is only focusing on driving, not collecting data. All right. Now the other two people are going to be collecting the data, where you're going to record at certain intervals. I think it's every 15 seconds. Your odometer reading and your speed. Okay. Now you're going to be starting off with your odometer and your speed at 0. So make it easier on yourself. Use the trip odometer, where you can zero that out, rather than using the big long odometer. You have to subtract 150,263 minus whatever. So use the trip odometer. Also, that'll give you the tenths, which is helpful. All right. So basically, what you're going to do is you're going to drive around for 10 minutes, record this data, and then you're going to create a graph like this. So due September 27th and 28th is this first part. The backside is due later. So do that first deadline. Is a table with your data. 1 to 2 paragraphs describes the route that you drove. Be specific with that. Explain where you went. And then individually, you're each going to make your own graph of the speed versus time. So you will be hand plotting those points and make a nice smooth curve with it. Now, as far as what you're turning in as a group, the group part of the project is really only to collect the data. So you guys can turn in the same data chart and the same description. You don't have to create your own data chart and same description. So you can photocopy that and turn that in. Everyone can turn that same thing, but each person in your group will be doing their own graph, and the backside will be their own work and everything. Now, as you work through it, feel free to check with the others in your group that you guys are getting the same answers to make sure you're doing right. And your answers might be a little bit different based upon kind of how you connect the points, but everyone will be turning in their own graphs. So let's see, you guys will be Thursday, I think. Thursday the 28th, I want from each person your data, your route, and your own graph. Now again, the data and the route, you're allowed to copy and photocopy from person to person. Before you give me your graph, you're going to make 4 copies for yourself. You can keep the original. I don't have to have the original. You can keep the original. I just need 1 copy, and then you need 4 for the second part of it. Your copies, will make sure you can still see the grid in the background. So you might want to trial run that, scan it, or copy it first to see that the grid lines come up, or choose a different grid paper. All right, so the second part, on your 4 separate graphs, one graph you'll be doing the left-hand sum, the next one right-hand sum, midpoint, and trapezoid. Now we'll briefly go over how to do this, probably next class, just so you can kind of get an idea. But the idea is that you're going to use certain intervals, draw rectangles, and find the area of each rectangle. Or down here for the part D, you're going to be drawing trapezoids and find the area, and then calculating that, totaling that up together. So again, this is each person at this point is doing their own work. It's fine to check with one another to make sure you're on the right track. And then there's the final question. Using your graphs, does the estimate for each method appear to be an under or overestimate in comparison to your actual distance you traveled from that odometer reading, and which estimate is closest to the distance traveled? So this second part will be turned in October 12th and 13th. And you can see the rubric breakdown for it. So again, the paragraph description and the data. I'll put those on there somewhere. The data and the paragraph description, that can be copied for everyone, but you should be turning in your own graphs with your own sums. Questions on this?
Does it have to be handwritten?
Your graph does need to be hand done. Yeah. If you want to type up your paragraph responses, though, that's perfectly fine. Other questions? All right, so go ahead and set that aside. And then now we'll move into limit definition group. All right, so this is what I passed out earlier. Go ahead and get that back out. All right, raise your hand if you've heard the words derivative or the word derivative before. Okay, figure about half of us. So today we're starting to touch our feet into the water of derivative land. We're going to just be looking at the limit definition of a derivative as we are in the limits unit, and then next unit we'll start going into derivatives and polynomials. So basically what a derivative is the slope of the tangent line to a specific point on a graph. Now we're going to go ahead and draw out some pictures to kind of investigate this. But you'll see kind of down here at the bottom, words that are equivalent to derivative, you'll see this word slope here. So you'll hear derivative referred to the bottom slope because it is the slope of the tangent line at the particular point, so it's the slope at that point. All right, if you think of, let's just say, an x squared graph. Just a plain old x squared graph. What type of slope do I have over here? A negative slope. And would you agree this is a large negative number, and then as I get closer to 0, it becomes a smaller negative number? And then what is my slope at 0? 0. And then as I continue down, if I continue to do lots of little slopes here, what does my slope become on the right side? It's positive. And would you agree it's a small positive number that gets to be a larger positive number? Okay. So what the derivative does is the derivative of a function gives us another function that will give us the slope at any point on the line here. So if I found the derivative of this graph and said, what is the derivative at -1? I could take -1, put into my equation, and it would pop out exactly what the slope is at that point. If I put in 0, it would pop out as a slope of 0. Now what we're looking at today is the limit definition of a derivative, so we're not learning quite yet the rules for it. Now you might see the different derivative rules as you're doing your work today. You might see kind of patterns. And I encourage you to kind of look for those patterns. As you are doing these, you might be able to recognize what some of those derivative rules are. So before we go down that road of actually the limit definition, let's take a look at secant line, tangent line, and how our secant line can help us find our tangent line. So secant, you've used that word back in geometry. You probably haven't used it since then. Secant line is a line through 2 points. So here we have a graph. The line going through points A and point B. Would you agree if we were given a little bit more information, we could find the slope of that secant line? Yeah. Looking at this, I don't know, good guess might be like +1, 2. So we know it's a positive slope here. Now, a tangent line is where the line touches the graph only at one point. In geometry, you were doing this with circles where we would have secant line or secant segment, and then we would have a tangent line or segment here. So tangent intersected the circle at one point, secant intersected it at 2 points. Here we're talking about tangent and secant lines to a graph. So secant intersects the graph twice, tangent gets the graph at just that one point. Now, if I take that secant line, if I get point A and I move point A closer to point B, and then I draw my secant line again. And then I draw it again even closer. And draw that secant line again. And then move it even closer. And again, draw that secant line again. Would you agree that as I move my point A closer to point B, that secant line gets closer and closer to my actual tangent line? As we close that gap between the two x values, that slope becomes closer and closer to the actual slope of the tangent line. And that's what this third column here is showing. As we move our A value, our A point closer and closer to B, those secant slopes are going to get closer and closer to the actual tangent slope. Now for this one, it's easy to figure out our tangent slope. It is 0 there. But it's not always going to be 0. So as the secant line connecting point A to point B, the closer A gets to B, the more the secant line looks like the tangent line. All right, so let's go ahead and draw a picture kind of detailing this. I think I want to get rid of this. All right, so let's go ahead and draw a nice curve here. I'm going to kind of illustrate what's happening with our limit definition here. All right, let's just go like this. And let's pick x here. So then we would say this is f of x. And let's go with h here. So what we're going to do is, this is my x value. Now you'll notice here it says x plus h, so I'm going to go h, we're going to call this h distance away, so this would be x plus h. I don't know what that distance is, so we're going to call it h, maybe it's 2 away, 3 away, 5.8, but x, and then the distance x plus h. So then this would be f of x plus h. Alright, so the limit definition derivative, again, comes back to slope. What is the formula for just slope of a line? Good. Well, y equals mx plus b is my slope-intercept form, but what's the formula for just slope? Good. y2 minus y1 over x2 minus x1. Subtract your y's, divide by your x's, subtract it. So if we go ahead and draw our secant line here, do your best with drawing it. If I draw my secant line and find the slope of the secant line, my slope of that secant line is going to be, so my y value, so y2, and that y value is f of x plus h, minus y1, and that y1 value is f of x. So again, y minus y over x minus x. And this first x is x plus h minus x. I was just saying the slope of the secant line is 2c. So if I were to find the slope of my secant line here going through those two endpoints, y minus y over x minus x. Now what do we see happens with that denominator there? Yeah, the x's cancel out, left with just h. Alright, so if I were to rewrite the slope, I'd have f of x plus h, some y value, minus some other y value, over that h. Now, like we said, if I got these points closer and closer together, so let's say I'm interested in trying to find the slope actually at x. As I move this closer and closer together, then I'm going to get that slope closer and closer to the actual tangent line. So again, if we kind of investigate here, let's go ahead and just put it pretty close to it. So say this is my new x plus h. This would be my new f of x plus h. Would you agree that this secant line is much closer to the actual tangent line? do your best to actually draw the real tangent line at that point x. And it's difficult. Okay, so notice how as we get that second endpoint closer and closer to the one we're investigating, that secant slope is going to be very close to that tangent slope. So what's happening to h as we get those values closer? What is happening to that h value? It's getting smaller. Here h was larger, we're getting it smaller and smaller and smaller. So if we get h closer and closer to 0, would you agree that our secant line would get closer and closer to that tangent line? And thus the slope of secant would actually become the slope of tangent. So as we got our h value to be closer and closer to 0, then we would have the slope of what would be the tangent line. And that's what this first one here is. The limit as h approaches 0, so as the distance between the 2 points gets smaller and smaller and smaller, the limit of that slope is going to be the slope of that tangent line. As h gets closer to 0, then we get the slope of that actual tangent line. So this first one is going to be the slope, or sorry, the derivative for a function. So I could take that function x squared and use that limit definition to find what the actual derivative is. I could tell you right now that it's 2x. The second one, this is for the derivative at a point, at a specific point. So if I were looking specifically at, let's say, x approaching 2, at that point 2, then we would use that technique. Today we're going to be dealing mainly with that first one. Again, we're going to be doing this is the long way to find your derivative. It's painful, but you'll make it through. And once we learn our derivative rules, you don't have to keep doing this unless the question specifically asks for that. But this allows us to find the derivative of really any function that does have a derivative. Yes?
What is the blue ring saying?
So this is x plus h, f of x plus h. This is simply, I'm moving my point closer to x, so I said, okay, well, let's take a look as it gets closer, what would my secant line look like? So it's really a different h value, if you want to put like h1 or something. Okay, so notation of words that are equivalent to derivative. We've already talked about how slope is kind of synonymous with it, although we're talking about slope of the tangent line. And since slope is rate of change in y over change in x, that's another one. Rate, velocity. Now, velocity itself does not mean derivative, but velocity is the derivative of the position function. If you've taken physics, you maybe remember that from it. If you haven't taken it, you'll learn that in physics. So velocity by itself does not mean derivative, but when we're looking at position functions, that is the derivative of the position, so that's why you'll hear that a lot with it. Now, our notation here. This we read as f prime of x. That means the derivative of our function. So the derivative of f of x is f prime of x. If it was g of x, it would be g prime of x, h of x, h prime of x. This is some more notation for derivative, dy dx. So this is the derivative of y with respect to x. Say it was j equals b dj dx. For right now, we're going to just be doing derivatives with respect to x. When we get some implicit differentiation, we'll do it also with respect to y. Again, if it is y equals, you can just say y prime. So function notation with the f prime of x, when it's just in that algebra 1 notation of y equals, then a y prime. And then lastly, we have this one, d dx of f of x. So you might see like d dx of x squared plus 3. Maybe they did not define that f of x was x squared plus 3 in the first place. This means take the derivative of this function. Now what you could do is just simply say let f of x equal x squared plus 3 and then write f prime of x. But all three of these mean derivative, or take the derivative. Questions on that notation? Okay. So let's go ahead and take a look at doing this limit definition of the derivative. And we'll start off with a couple basic ones. And again, this is going to feel long and tedious. It is. But this is what's happening behind the scenes when we learn this derivative rules. This is what allows us to acquire average root. Okay, so we're going to go ahead and again use, and I want you to write at the top of your paper because you're going to need to have those limit definitions memorized. So the limit is x h. We're using the h approaching 0. As h approaches 0, of f of x plus h minus f of x over h. So the limit as h approaches 0, because we want that h to get smaller and smaller. And if we took this and did direct substitution, I would get f of x minus f of x, so 0 over 0, and that's going to be that issue, that indeterminate. So we have to do some algebraic manipulation with it. All right. Now, it might be helpful for you. Since we have to do f of x plus h. Some students find it's helpful to go ahead and in the beginning write what x plus h is. And in this case, it'd be 2 times x plus h, right? Wherever x is, we're substituting x plus h. Just like your composition of functions, you would take g of x and shove it in for x. You're taking x plus h and shoving it in. All right, so find the derivative of f of x. So our derivative notation would be f prime of x. F prime of x. It still does not. All right. So my derivative is equal to the limit as h approaches 0 of f of x plus h, so we have 2 times x plus h, minus f of x, which is 2x, over h. Okay, so in f of x plus h, so 2 times x plus h, minus 2x over h. Now again, if we put in 0 for h, it's still going to give us issues. So let's go ahead and simplify and manipulate it, see if we can do something. So distributing our 2, we would get the limit as h approaches 0. So 2x plus 2h minus 2x over h. And what do we see happens if we look at it? Okay. We get these to simplify. So the limit as h approaches 0. I end up with 2h over h. Does it do anything more from that? And h is reduced. So this is really just the limit as h approaches 0, 2. And what is the limit of 2? 2. So f prime of x, for this particular function, the derivative of 2x anywhere is just 2. Which, if you think about this, what does my graph 2x look like? It's a straight line with slope what? 2. Does the slope ever change? So wouldn't your slope be 2 anywhere along there? Now, it's not always going to just be a single number, because think about sine. Look at how many different places that has a slope. There are different slopes. All right, now here I wrote out every single step, right? But we talked about how we can do some algebra in our head. So I expect to see this first step where you write out with it having the function with x plus h. But here I trust that you could go ahead and cross this all out and get it down to just limit equals 2. Okay. So again, you don't throw it out every single step, but I need to see that starting and somehow to break manipulation. Yeah.
So when we get to the AP test, do they have to do it like this?
Yeah. So now this isn't going to be a very common question because by the time it gets to the debate, it'll be much more exciting to ask you. But they might ask you to find the derivative using that limit definition, in which you would go ahead and do it this way. But for response, that would only be like 1 part response they put this there. Yes.
I think I missed this. So the f with the dash, that always means derivative.
Yes. Yep. So we call that maintenance. Yeah, it's basically an apostrophe. Now this means first derivative. If we have two of them, that means the second derivative, which means you take the derivative again, or the third derivative, or the quarter, so on and so forth. Yeah. Other questions on this? Okay. So let's try example 3. A little more exciting. There's an x squared in it. Alright, so example 3, it says find the derivative of f of x, and then find f prime of negative 2. Alright. Well, before we can find f prime of negative 2, we need to find f prime. So we've got to first find the derivative. So f prime of x equals. So again, the limit is h approaches 0. So f of x plus h, this is one where it might be kind of hard for you to put it in right away. So if you want to write what f of x plus h is up here, that might be helpful for you. So we get 3 times x plus h squared minus 7. So that whole thing is our f of x plus h. Minus, and you want to be careful here, we're subtracting the entire f of x. So use parentheses, save yourself from heartache of forgetting to distribute that negative. All over h. So again, this first piece here, this is my f of x plus h. My second piece here, that's just my f of x. So f of x plus h minus f of x. Alright, let's go ahead and multiply, simplify. You do it there, I'll do it up here. Let's reconvene when we get to simplify. We should have got it down to at least this. 3h squared plus 6hx over h. Did we at least get to this one? Okay. Now if I substitute in 0, I'm still going to have the issue of 0 to 0. What could I do to simplify this? Back out an h. And again, you could have gone from this step to this step without running the simplified there. The limit is h approaches 0 of h times 3h plus 6x over h. Now my h is reduced. And if I do direct substitution here, I take 0 and put it in, what do I get? 6x. So f prime of x is 6x. And when we learn our power rule with polynomials, you'll learn that you into it very quickly without any of that algebraic manipulation. Questions on that? Again, it's long and tedious right now. It's just something you have to do. And so we get to those. Now, we found our derivative, but now we have to find f prime of negative 2. What do you guys think we do to find that? Just substitute in negative 2.
Could you pull out a 3?
That's a good question. Yeah. Yeah, then you would have still had the 3 multiplied by 2x. Yeah. Alright, so we want to find, was it f prime of 2? Positive? Negative 2? Okay. F prime of negative 2. So 6 times negative 2. So negative 12?
Yeah.
Okay. Alright. Questions on that one? Okay. Now, for example 4, it says find the derivative, and then it says find the slope of the tangent line at x equal to 3. What does that mean, the slope of the tangent line? What does that mean? The derivative, right? The slope of the tangent line is your derivative. So this is just another way to say find the derivative at 3 or find f prime of 3. Just another way to say it. Alright, questions on that? Okay. Let's go to, I want you guys to go and try example 8. It's less work than yourselves. So go and try example 8. Alright. Should have gotten it down to 1 over root x, which when we rationalize root x over x. Here our conjugate looks a little crazy, but again, the only thing that you change is that sign in between the radicals. Be careful with your multiplying. If you wrote 2 here, you made the same mistake I did, forgot to multiply 2. So just be careful as you're distributing it all out. And then we had our 4x's cancel, our h is reduced. So we had the crazy conjugate in the denominator, but it wasn't too bad unless we plugged in that 0. Any questions on that? Yes.
How come that doesn't become like a, when you cancel out the h's, how come it doesn't become like a 3h?
3h. So 4h for h. This part. So remember, anything divided by itself is just 1. So like,
How do you have like a variable and how do you distribute? Or is that for
exponents, yeah. So if I had like h to the 5th and h squared, then you subtract your exponents. Okay. Yes.
How did you get 4 over 4
So my 4x's cancel here, and then I had 4h over h times that, so I reduced my h's, which left with just 4 in the top. I combined a lot of that. Other questions with this? And again, guys, if you want to write, like separate and write work over here, and like go ahead and define what f of x plus h is and simplify that. If you want to do your conjugate stuff over here, that's fine, but again, I need to see all the work somewhere in between. So keep writing limit until you've actually evaluated the limit, which means you use the knowledge that you have the bottom heavy, top heavy balanced, or a special trig sub, or when you do direct substitution. So we hadn't taken the limit yet, so we needed that limit notation, but here I didn't do that direct substitution, so then I could get rid of that limit notation. Questions on that?
Something I tried, but didn't, honestly, but can you square root on the back?
Square root?
Just square them.
Can you say that again?
Like, so like, put the whole equation in parentheses and then the second.
Oh, you want to take this whole thing and square it?
Like the top one,
Here.
yeah. I think we're gonna, like, I know, like, it's more complicated.
The answer is no, because what you're doing is you're changing what function you're taking the limit of. So here we're taking the limit of this function. What you're doing is taking the limit of this function squared. So it's kind of like if I had like the expression 5 plus 3. I can't just suddenly say, well, let me just square that. I can use that as a tool to solve an equation where I like square both sides. But we're algebraically technically we're simplifying it. You can't just take a square out of nowhere. That changes the value of the equation. Does that make sense? The difference there? Other questions? Okay, so real quick, let's go ahead and look at example 11 and 12. So here it says each limit represents the derivative of some function at some number. State the function in what number it's approaching. So remember, our limit notation was a limit as h approaches 0 of f of x plus h minus f of x over h. So here they've actually substituted in a value, and they didn't tell us what the function is. So if we look at this, you can probably guess, what is the x value that we're substituting in? 3. Okay, so let's go ahead and state that x is 3. Alright, but what is my function then? And usually for these, it's easiest to look at your f of x plus h, because since the number is substituted in, it's kind of hard to figure out what function gave you 81. But so replace that number, we know that number is 3, so that's the idea of x plus h. So what was my function then? X to the 4th. So my function was f of x equals x to the 4th at x equal to 3. We can see then x plus h to the 4th, 3 plus h to the 4th. And if you think about it, 3 to the 4th is 81, which is what that is there. So likewise over here. Again, what would that function be? Again, think of this in terms of x plus h. What is my function? 3. That's good. So then when I substitute in x plus h, I'd have 3 x plus h. And what value are we looking at? 4. All right, go ahead and try 13 and 14. It might not always be that they actually take that value and substitute it in. It might just be the function. But you can kind of see how you can identify that. homework and passing out to big by homework. As you can tell, tedious with all that limit notation, but it's good for you. What do we get for our function for number 13? Okay, x to the 7th. And what was the x value that we're looking at? Good. And then what did we get from number 14? Good, percent x. And what value are we looking at? Thanks. One more. Anyone else not here? Have a good day. You have TA and Stinger 1. SR&R day.